Now, in this lecture, we find out the radius of a circle using two different methods. In the drawing, we have a triangle ABC that blocks the circle, or the circle is inscribed by triangle ABC. In addition, we know that this angle ABC equals to 60 degrees in its size, and this angle ACB equals to 75 degrees, and side BC of this triangle ABC equals to 2 units in its length. Again, our mission is to find out the radius of this circle. So we start with the first method, and we will do here a construction, that is to say from point C, we will draw perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. By doing this construction, we created here the right triangle BDC. So I'll copy the right triangle BDC in a new page and we will analyze it. So actually, this is the right triangle BDC that I copied from the original drawing. BC equals to 2 and this angle DBC equals to 60 degrees according to what is given as the question. So in the right triangle BDC, cosine 60 degrees equals to BD over BC. So it is BC and BD over BC, and BC is 2, so cosine 60 degrees equals to BD over 2. Cosine 60 degrees is 1/2, so we substitute cosine 60 degrees by 1/2. So 1/2 equals to BD over 2. Here we multiply this equation by 2, and finally we get that BD equals to 1 unit in its length. So this line segment BD is equals to 1 unit in its length. we'll continue to focus on the right triangle BDC. So the right triangle BDC, sinus 60 degrees equals to DC over BC. Sinus 60 degrees is equal to 3 over 2, and it is equals to DC over BC, and BC is 2. So in conclusion, found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2. And finally we get that DC equals to the square root of 3 units in its length. So here DC equals to the square root of 3 units in its length. So in the sum right triangle BDC, the sum of the angles must be equal to 180 degrees. So which angles we have inside the right triangle BDC? This angle equals to 60 degrees. This angle is a right angle, so 60 degrees plus 90 degrees, it is 150 degrees. And therefore the missing angle here must be equal to 30 degrees in its size. Again, in order to complete the sum of the angles in this right triangle BDC to 180 degrees, the missing angle here must be equal to 30 degrees in its size. So according to what is given us in the question, the big angle ACB equals to 75 degrees in its size. This is the big angle ACB, this is equal to 75 degrees. Angle BCD, the small angle, equals to 30 degrees. So the missing angle, from the drawing, it is very easy to see that the missing angle ACD this is the missing angle ACD. The missing angle ACD equals to the big angle minus the small angle. So the big angle is 75 degrees, the small angle is 30 degrees. 75 degrees minus 30 degrees, it is 45 degrees. So the missing angle ACD equals to 45 degrees in size. In the next step, I will copy the right triangle ADC in a new page and analyze it. So actually, this is the right triangle ADC that I copied from the original drawing. We've already found out that DC equals to the square root of 3 units. And this is the missing angle that we found, that is equals to 45 degrees in its size. We know that the sum of the angles in any triangle, and especially in the right triangle ADC, must be equal to 180 degrees. So which angles we have inside the right triangle ADC? This angle equals to 45 degrees, plus this angle that is 90 degrees. 45 degrees plus 90 degrees is 135 degrees. Therefore, the missing angle here must be equal to 45 degrees in its size. So those two angles are equal to each other, and we have the rule that in front of equal angles in the triangle there are equal sides. So in front of those two equal angles we have those two sides that must be also equal to each other. That is to say, side AD must be equal to side DC, but we have already found out that DC equals to the square root of 3 units, so we can write here that DC equals to the square root of 3 units, and for this equation AD equals to DC equals to the square root of 3 units, we will conclude that AD also equals to square root of 3 units in its length. AD, side AD equals to the square root of 3 units in its length. You can write down in the original drawing that one segment AD equals to the square root of 3 units in its length. We will continue to focus on this right triangle, triangle ADC. According to the Pythagoras theorem, in the right triangle, triangle ADC, here by PT is the abbreviation for Pythagoras theorem. According to the Pythagoras theorem, in the right triangle ADC, AC square, that is the square of the hypotenuse, must be equal to AD square plus DC square. So AC square equals to AD square. AD is equal to 3, therefore AD square is equal to 3 square, that is 3, plus DC square. DC is also equal to 3, therefore DC square is equal to 3 square, that is 3. So in total, AC square equals to 3 plus 3, that is 6. AC square equals to 6. We will take a root out of this equation, and finally we get that AC equals to the square root of 6 units in its length. Side, the hypotenuse AC equals to the square root of 6 units in its length. Here, side AC of triangle ABC equals to the square root of 6 units in its length. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is inscribed by triangle ABC, that could be any triangle, the radius R equals to the area of triangle ABC that blocks the circle over S. S is the semiperimeter of triangle ABC that blocks the circle, and the semi-perimeter of any triangle equals to the perimeter over 2. So the drawing of rule number 15, this is the drawing of rule number 15. We have here a circle that is inscribed by this triangle, triangle ABC. So the radius R of this circle, according to this rule number 15, the radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. So we can actually implement rule number 15 in our drawing. Why? Because whenever you have a circle that is inscribed by triangle, you can implement rule number 15. We have here a circle that is inscribed by triangle ABC. So according to rule number 15, we define the radius of this circle as R. So the radius R of this circle, according to rule number 15, will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. I repeat again. According to rule number 15, the radius R of this circle that is inscribed by this triangle, triangle ABC, will be equal to the area of this triangle, triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Okay. We know that the area of any triangle equals to the base of the triangle times the height to the base over 2, and we have to divide the area by S. That is the semi-perimeter of the same triangle, triangle ABC. So we choose the base of this triangle, triangle ABC as AB. So the base is AB. The height to the base must create 90 degrees with the base, therefore the height is CD because it creates 90 degrees with the base, AB. So the height is DC, all divided by 2, and we have to divide the area by S, that is the same perimeter of the same triangle, triangle ABC. So we have already found out that AB equals to the square root of 3 plus 1. Times DC. DC equals to the square root of 3 units. All divided by 2. So this expression is the area of triangle ABC, and we have to divide the area of triangle ABC, this expression, by S. S is the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of any triangle is the perimeter over 2, and the perimeter of this triangle, triangle ABC, is AB plus AC plus BC. Again, AB plus AC plus BC, and if you divide the perimeter by 2, we get the semi-perimeter S. So the area, the radius R of this circle equals to square root of 3 plus 1 times square root of 3 divided by 2, that is the area of triangle ABC, all divided by S. S equals to AB, and AB is square root of 3 plus 1 times AC. AC equals to the square root of 6 units plus BC. BC equals to 2 units according to what is given as the equation, so it is plus 2 all divided by 2. So actually this expression in total is equal to the semi-perimeter S of our triangle ABC, and this expression in total it is equal to the area of triangle ABC. So actually the value of this expression, that is the area of triangle ABC, is 2.366. That is to say, the area of triangle ABC equals to 2.366 square units divided by semi-perimeter S. The semi-perimeter is this expression, and the value of this expression in total it is equal to 3.591. Okay, again the semi-perimeter of triangle ABC equals to 3.591 units, and 2.366 over 3.591 equals to 0.6589. So in conclusion, found out that the radius R of this circle equals to 0.6589 units. And that is the answer to the question. Repeat again. The radius R of this circle equals to 0.589 units. So we finished with the first method. In the next step I present to you how to find out the radius R of this circle according to the second method. Repeat again, we have to find out the radius R of this circle that is described by triangle ABC. So we define the center of this circle, this point is O. We define the point of tendency of tangent BC with this circle is D. Here point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of this circle that we define as R, so OD equals to R. We join points O and D together by a straight line. We define the point of tendency of tangent AC with this circle as F. And we define the point of tendency of tangent AB with this circle as E. We join points O and F together by a straight line. Line segment OF is the radius of this circle that is equal to R according to our definition. We join points O and D together by a straight line. Line segment OE is also the radius of this circle that is equal to R. Here we can implement rule number 1. according to rule number 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. In the drawing we have tangent AB. This is tangent AB. That is tangent to this circle is point M. Point M is the point of tendency. And we also have the radius OM that is drawn to point M. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to this rule number 1. We can implement rule number 1 in our drawing. Why? Because in our drawing we have the radius OD that is drawn to point D. That is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule number 1. Likewise, we have the radius OF that is drawn to point F. And therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will also equal to 90 degrees. And we also have the radius OE that is drawn to point E, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius EO. That is to say, this angle will be equal to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule number 1. We can implement here also rule number 2. According to rule number 2, the length of two tangents from a common point to a circle are equal. So in the drawing we have a circle and this common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule number 2, they are equal to each other. That is to say, PA equals to PB. So we can actually implement this rule number 2 in our drawing. Why? Because in our drawing, if you focus on the common external point, point C, from the common external point, point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. So CF equals to CD according to rule number 2. I will write it down. 97 CF, tangent CF equals to tangent CD according to rule number 2. Likewise, we focus on the common external point, point B. From the common external point, point B, we have two tangents to this circle, tangent BE and tangent BD. And according to rule number 2, they are equal to each other. That is to say, BE equals to BD. So tangent BE equals to tangent BD according to the same rule, rule number 2. In the next step, we join points O and C together by a straight line. And we join points O and B together by a straight line. And we will prove that those two right triangles can go into each other. That is to say, we will prove that the right green triangle, triangle BOD, is congruent to the right yellow triangle, triangle EBO. So write it down. We prove that the green right triangle BOD is congruent to the right yellow triangle EOB. So, why the yellow triangle congruent to the green triangle? First of all, side EO of the yellow triangle equals to side OD of the green triangle. They're above the radii of the circle, therefore they are equal to each other. So write it down. Repeat again. Side EO of the yellow triangle equals to side OD of the green triangle. They're both equal to R because they are the radii of the circle, therefore they are equal to each other. In addition, we know we have side BE of the yellow triangle equals to side BD of the green triangle. Here, BE equals to BD according to rule number 2. Repeat again. Side BE of the yellow triangle equals to side BD of the green triangle according to rule number 2. And finally, side OB is a common side that belongs to both triangles, so we can write down that OB equals to itself. It's a common side that belongs to both triangles. Repeat again. OB equals to OB. It's a common side that belongs to both triangles. So actually prove that all the three sides of the yellow triangle are corresponding equal to all the three sides of the green triangle. Therefore proved that those two triangles can go into each other according to side rule. So I write it down. We proved that the yellow triangle EOB is congruent to the green triangle BOD according to side rule. Okay. Repeat again. the yellow triangle EOB can go into the green triangle, triangle BOD, according to side rule. And from the fact that those two right angles can go into each other, we derive that those two angles are also equal to each other according to the rule that corresponding angles and congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding angles, those two corresponding angles must be also equal to each other. So this is angle EBO in the green triangle. And it is equal to this angle OBD in the green triangle. So angle EBO equals to angle OBD. So if we define one of those two angles as theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees. That is to say 2 theta equals to 60 degrees. We divide this equation by 2 and we get that angle theta equals to 60 degrees over 2 is 30 degrees. Okay, angle theta equals to 30 degrees in its size. So this is angle theta that equals to 30 degrees in its size. In the next step, I will copy the green right triangle OBD in a new page and we'll analyze this green right triangle OBD. So actually this is the right green triangle OBD that I copied from the original drawing. Side OD is the radius of the circle that is equals to R, and this is angle theta that is equals to 30 degrees in size. So in this right triangle OBD, tangents 30 degrees equals to OD over BD. So tangents 30 degrees equals to OD. OD is R, so we substitute OD by R. So it is R over BD. You can inform them that tangents 30 degrees equals to R over BD. Here we multiply this equation by BD and we get that BD times tangents 30 degrees equals to R. Here we divide this equation by tangents 30 degrees and finally we get that BD equals to R over tangents 30 degrees. So actually this line segment BD equals to R over triangle 30 degrees. So write it down. BD equals to R over triangle 30 degrees. We repeat on the same process on those two right triangles. That is to say, we prove that the orange right triangle ODC is congruent to the pink right triangle OFC. So the orange triangle ODC is congruent to the pink triangle OFC. So why those two triangles congruent to each other? OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. In addition, CF equals to CD, according to rule number 2. Here, CF equals to CD according to rule number 2. And finally, side CO is a common side that belongs to both triangles, so we can write down that CO equals to itself. It's a common side that belongs to both triangles. So we actually prove that all the three sides of this right pink triangle OFC are correspondingly equal to all the three sides of the right pink triangle ODC. Therefore, we actually proved that those two right triangles can run to each other according to side rule. So write it down. The pink triangle OFC congruent. This is the sign of congruent to the orange triangle ODC according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So this is angle FCO in the pink triangle, and it is equal to this angle OCD in the orange triangle. Angle FCO equals to angle OCD. So if we define one of those two angles as alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha, that is 2 alpha, equals to 75 degrees. 2 alpha equals to 75 degrees. we divide this equation by 2, and finally we get that angle alpha equals to 75 degrees over 2, that is 37.5 degrees. So actually, this is angle alpha, that is equals to 37.5 degrees in its size. In the next step, I will copy the right triangle ODC in a new page and we will analyze it. So actually, this is the orange right triangle ODC that I copied from the original drawing. So side OD is the radius of the circle that is equal to R, and this is angle alpha that is equal to 37.5 degrees. So in this right triangle ODC, tangents 37.5 degrees equals to OD over DC. So it is OD is R, so it is R over DC. So tangents 37.5 degrees, in total it is equals to R over DC. Here we multiply this equation by DC, and we get that DC times tangents 37.5 degrees equals to R. Here we divide this equation by tangents 37.5 degrees, and finally we get that DC equals to R over tangents 37.5 degrees. So this line segment DC equals to R over tangents 45 degrees, so I write it down. From the drawing it is very easy to see that side BC of triangle ABC, BC equals to BD plus DC. Repeat again. BC equals to BD plus DC. BC equals to 2. Here, according to what is given in the question, BC equals to 2. So we substitute BC by 2. And it is equals to BD. BD equals to R over tangents 30 degrees. So we substitute BD by R over tangents 30 degrees. Plus DC. DC equals to R over tangents 37.5 degrees. So we substitute DC by R over tangents 37.5 degrees. So in conclusion, we found out that 2 equals to R over tangents 30 degrees plus R over tangents 37.5 degrees. So 2 equals to, here we take out r as a common factor from those two expressions. So what is left from this expression after we took from it r as a common factor? What is left? It is actually 1 over times 30 degrees plus what is left from this expression after we took from it r as a common factor? What is left is actually 1 over times 37.5 degrees. So in conclusion, I found out that 2 equals to r times 1 over times 30 degrees plus 1 over times 37.5 degrees. So 2 equals to r and 1 over times 30 degrees is 1.732 plus 1 over times 37.5 degrees. 1 over times 37.5 degrees is 1.3032. So 2 equals to r and 1.732 plus 1.3032 equals to 3.0352. So in conclusion, found out that 2 equals to r times 3.0352. We will divide this equation by 3.0352, and finally we get that r, the radius that we are looking for of the circle, equals to 2 over 3.0352, and 2 over 3.0352 equals to 0.6589 units. So we actually found out that the radius r of the circle equals to 0.6589 units. So actually, in both methods, we found out that the radius r of this circle equals to 0.6589 units. Okay, so in the next step, I will summarize the lecture. We'll start with the first method, of course. In this lecture, we found out the radius r of this circle that is described by this triangle, triangle ABC. So, in the drawing, we have a circle that is described by triangle ABC, or triangle ABC blocks the circle. We know that angle ABC, this angle equals to 60 degrees in its size, and this is angle ACB, that is equals to 75 degrees. In addition, we know that side BC of this triangle, triangle ABC equals to 2 units in its length, and our mission is to find out the radius r of this circle. So, in the first method, we did a construction, that is to say, from point C we draw perpendicular on side AB. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C in AB as D. By doing this construction, we created here the right angle CBD. So I copied the right angle CBD in a new page and we analyzed it. This is the right angle CBD that I copied from the original drawing. Angle DBC equals to 60 degrees and BC equals to 2 according to what is given in the question. So in the right angle DBC, cosine 60 degrees equals to DB over BC. So it is dB over BC, and BC is 2, so we substitute BC by 2. And finally found out that cosine 60 degrees equals to dB over 2. Cosine 60 degrees equals to BD over 2. Cosine 60 degrees is 1/2. So 1/2 equals to BD over 2. We multiply this equation by 2 and finally found out that BD equals to 1 unit since length. Here, this right segment BD equals to 1 unit since length. We continue to focus on this right angle, triangle DBC. Here, sinus 60 degrees equals to DC over BC. Okay, that is to say, here sinus 60 degrees is equal to 3 over 2, and it is equals to DC over BC, and BC is 2. So in conclusion, found out that square root of 3 over 2 equals to DC over 2. Here we multiply this equation by 2, and finally found out that DC equals to the square root of 3 units since length. Here, this time segment DC equals to the square root of 3 units in its length. In the same right triangle DBC, the sum of the angles must be equal to 180 degrees. So which angles we have inside the right triangle DBC? We have this angle that is 90 degrees plus this angle that is equal to 60 degrees. 90 degrees plus 60 degrees, it is 150 degrees. Therefore, the missing angle here must be equal to 30 degrees. Okay? It is given as in the question that the big angle ACB equals to 75 degrees. We just right now found out that the small angle DCB equals to 30 degrees. So the big angle minus the small angle equals to the missing angle ACD. Again, the big angle minus the small angle equals to the missing angle ACD. The big angle equals to 75 degrees, the small angle is 30 degrees, so the missing angle is 75 degrees minus 30 degrees, that is 45 degrees. This is the missing angle that is equals to 45 degrees in its size. Then I copied the right triangle ACD in a new page and we analyze this right triangle ACD. This is triangle ACD that I copied from the original drawing. We just right now found out that this is the missing angle that is equals to 45 degrees in its side. This angle equals to 90 degrees according to our construction. The sum of the angles in this right triangle ADC must be equal to 180 degrees, so 45 degrees plus 90 degrees is 135 degrees, therefore the missing angle here must be equal to 45 degrees. Okay? So I actually found out that those two angles are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, they are equal sides. So those two sides that are located in front of those two equal angles must be also equal to each other. That is to say, side AD equals to side DC. AD equals to DC, but we have already found out that DC equals to the square root of 3 units. So we can write here that DC equals to the square root of 3 units, and from this equation AD equals to DC equals to the square root of 3 units, we derive that AD also equals to the square root of 3 units in its length. Here, this is side AD, this is equal to square root of 3 units in its length. We can write here that AD equals to the square root of 3 units in its length. We continue to focus on the right triangle ADC. In the right triangle ADC, according to the Pythagoras theorem, AC squared equals to AD squared plus DC squared. Again, AC squared equals to AD squared plus DC squared. AC squared, that is the square of the hypotenuse, equals to AD squared. AD is equal to 3, therefore AD squared is equal to 3 squared, that is 3, plus DC squared. DC is equal to 3, therefore DC squared is equal to 3 squared, that is 3. So in total, AC squared equals to 3 plus 3, that is 6. AC squared equals to 6. We took out of this equation and finally found out that AC equals to the square root of 6 units. Here, side AC of this triangle ABC equals to the square root of 6 units in its length. In the next step, I presented to you a new rule and we implemented the new rule in our drawing. The new rule is rule number 15. According to rule number 15, the radius of a circle that is described by triangle ABC that could be any triangle, the radius R equals to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The semi-perimeter of any triangle is the perimeter over 2. This is the drawing of rule number 15. So in the drawing we have a circle with radius R that is inscribed by this triangle, triangle ABC. So the radius R of this circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. We can actually implement rule number 15 in our drawing. Why? Because in our drawing we have also circle that is inscribed by this triangle, triangle ABC. Whenever we have a circle that is inscribed by triangle, we can implement rule number 15. So in our drawing, we get that the radius R of this circle, according to rule number 15, will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. Repeat again. In our original drawing, according to rule number 15, the radius R of the circle will be equal to the area of triangle ABC that blocks the circle over the semi-perimeter of the same triangle, triangle ABC. The area of any triangle equals to the base of the triangle times the height to the base over 2, all divided by S, that is the semi-perimeter of the same triangle, triangle ABC. We choose the base of this triangle ABC as AB, and therefore the height to the base is CD, all divided by 2. The base is AB, the height to the base is CD, divided by 2, all divided by S, that is the semi-perimeter of the same triangle, triangle ABC. We have already found out that AB equals to the square root of 3 plus 1, and DC is equal to 3 divided by 2, and the semi-perimeter of our triangle, triangle ABC equals to the perimeter over 2. The perimeter is AB plus AC plus BC, and if we divide the perimeter by 2, we get the perimeter S. So the area of triangle ABC equals to this expression divided by S, and S is AB. AB is equal to 3 plus 1. AC is equal to 6, and BC is 2, all divided by 2. This expression is the semi-perimeter S of the same triangle, triangle ABC. The value of this expression, that is the area of triangle ABC, equals to 2.366, and the value of this expression, that is the semi-perimeter S of triangle ABC, is 3.591, and 2.366 over 3.591 equals to 0.6589. Therefore, the radius R of this circle equals to 0.6589 units. We finished with the first method. In the next step, I presented to you how to find out the radius R of this circle according to the second method. In the second method, we defined the center of this circle here as O. We define the point of tendency of tangent AB with this circle as E. We define the point of tendency of tangent AC with this circle as F. And finally, we define the point of tendency of tangent BC with this circle as D. Point O is the center of the circle, point D. We join points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself. Therefore, OD is the radius of this circle that is equal to R according to our definition. We have the radius OD that is drawn to point D, that is the point of tendency BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius DO. If BC is perpendicular to DO, then this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. Likewise, we join points O and D together by straight line. OE is the radius of this circle, is equal to R. The radius OE is drawn to point E. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle also equal to 90 degrees. Likewise, we join points O and F by straight line. OF is the radius of this circle that is equal to R. The radius OF is drawn to point F, that is the point of tendency of tangent AC with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius FO. If AC is perpendicular to FO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the same rule number 1. Then implemented here rule number 2. If you focus on the common standpoint point C, from the common standpoint point C, we have two tangents to this circle, tangent CF and tangent CD. And according to rule number 2, they are equal to each other. CF equals to CD according to rule number 2. Then we focus on the common standpoint point B. From the common standpoint point B, we have two tangents to this circle, tangent BD and tangent BE. And according to rule number 2, they are equal to each other. That is to say, B equals to BD according to rule number 2. Then we join points O and C together by straight line, and we join points O and B together by straight line. Then we proved that the yellow triangle is congruent to the green triangle according to side rule. So why those two triangles congruent to each other? First of all, side EO equals to side OD, they are both the radii of the circle, therefore they are equal to each other. In addition, BE equals to BD according to rule number 2, BE equals to BD. And finally, side OB is the common side that belongs to both triangles. So side OB equals to itself. So actually prove that all the three sides of the yellow triangle EBO are corresponding equal to all the three sides of the green triangle OBD. Therefore, those two right triangles can go to each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other. That is to say, we derive that angle EBO equals to angle OBD. So if we define one of those two angles as theta, then the other angle must be also equal to theta because they are equal to each other. So theta plus theta equals to 60 degrees. That is to say 2 theta equals to 60 degrees. We divided this equation by 2 and finally found out that theta equals to 30 degrees. This is angle theta that is equal to 30 degrees in its size. Then I copied the right green triangle ODB in a new page and we analyze this right green triangle ODB. This is the right triangle ODB that I copied from the original drawing. This is angle theta that is equal to 30 degrees in size. And DO is the radius of the circle that is equal to R. In the right triangle ODB, times 30 degrees equals to OD over BD. OD is R, so times 30 degrees equals to R over BD. Here times 30 degrees equals to R over BD. Here we multiplied this equation by BD and found out that BD times 30 degrees equals to R. Then we divided this equation by times 30 degrees and finally found out that BD equals to R over times 30 degrees. Here BD, this time segment BD equals to R over times 30 degrees. We repeated on the same process on those two, the right triangle and the pink triangle. We proved that those two right triangles can go into each other according to side rule. I repeat quickly on the proof. OF equals to OD, they are both the radii of the circle, therefore they are equal to each other. In addition, CF equals to CD according to rule number 2, here CF equals to CD according to rule number 2, and finally, CO equals to itself as a common side that belongs to both triangles. So proved that all the three sides of the pink triangle OFC are corresponding equal to all the three sides of the orange triangle ODC, therefore those two right triangles can go into each other according to side rule. And from the fact that those two right triangles can go into each other, we derive that those two angles must be also equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if one of those two angles is alpha, then the other angle must be also equal to alpha because they are equal to each other. So alpha plus alpha equals to 75 degrees. That is to say 2 alpha equals to 75 degrees. So alpha equals to 75 degrees. We divided this equation by 2 and finally found out that alpha equals to 37.5 degrees. So actually, this is angle alpha, this is equals to 37.5 degrees. Then I copied the right triangle ODC in the new page. We analyze this right triangle ODC. This is the right triangle ODC that I copied from the original drawing. Side OD equals to R, it is the radius of the circle, and this is the angle alpha that is equal to 37.5 degrees. In this right triangle ODC, triangle 37.5 degrees equals to OD over DC. Triangle 37.5 degrees equals to OD over DC. OD is R, so it is R over DC. So tan is 47.5 degrees equals to R over DC. We multiply this equation by DC and found out that DC times tan is 47.5 degrees equals to R. We divided this equation by tan is 47.5 degrees and finally found out that DC equals to R over tan is 47.5 degrees. Here, this line segment DC equals to R over tan is 47.5 degrees. It is very easy to see from the drawing that BC equals to BD plus DC. Again, BC equals to BD plus DC. BD plus DC. Here, BC equals to BD plus DC. BC equals to 2, according to what is given us in the question. So we substitute BC by 2. BD is R over tan 30 degrees plus DC. DC is R over tan 37.5 degrees. So in conclusion, found out that 2 equals to R over tan 30 degrees plus R over tan 37.5 degrees. So 2 equals to, we took R as a second factor from those two expressions. So what is left from this expression after we took from it R as a second factor? What is left? It is actually 1 over tan 30 degrees. What is left from this expression after we took from it R as a second factor? What is left? It is actually 1 over tan 35 degrees. So in conclusion, found out that 2 equals to R times 1 over tan 30 degrees plus 1 over tan 37.5 degrees. So 2 equals to R and 1 over tan 30 degrees is 1.732 plus 1 over tan 37.5 degrees is 1.3 is 1.30332. So in conclusion, found out that 2 equals to R times 1.732 plus 1.3032. So 2 equals to R and 1.732 plus 1.3032 equals to 3.0352. So 2 equals to R times 3.0352. We divided this equation by 3.0352 and finally found out that R, the radius that we are looking for, the radius of the circle R equals to 2 over 3.0352, that is actually 0.6589 units. So in both methods we found out that the radius R of this circle equals to 0.6589 units. Okay, thank you very much.